When you scan one of these, your phone turns it into a link in a heartbeat. We do it without thinking. But now rip a whole corner clean off it. Properly destroy part of it. Scan it again, and the very same link appears. Perfect. The squares are gone. So where on earth did the link come from? The answer is a genuinely beautiful piece of math from 1960. And the best way to truly get it is to forget QR codes for a minute and shrink the whole problem down to something tiny. Say I want to send you just two numbers, a 3 and a 5, down a connection that randomly drops things along the way. How do I protect them so that even if some of my signal gets lost, you still get my two numbers? Here is the trick. Instead of just storing them, I plot them as points on a graph. The position along the bottom says which number it is. The height says its value. So the 3 goes here and the 5 goes up here. And through 2 points, there's exactly one straight line. So those two numbers really are just this one line. Now here is the clever move, and it is the whole secret. A straight line only needs 2 points to draw it. So instead of sending just my 2, I send 4, and I make sure all 4 sit perfectly on that same line. The 2 extras are pure spares. I send all 4 down the wire, and sure enough, the bad connection drops 2 of them along the way. But watch what happens. The 2 points that survive still fix the exact same line. There's only one straight line that passes through them. And the instant I have that line back, I just read off the height at each position. The first is 3, the second is 5. Both numbers recovered perfectly, even though half of what I sent got lost. Those spare points were a safety net. That is the entire idea. Now we just scale it up. Your link is not 2 numbers, it is hundreds of them. So instead of a straight line, we use a curve. And a wigglier curve can simply carry more numbers. But the rule never, ever changes. A curve is pinned down by a certain number of points, and you always sample and send a few more than that, as spares. Now, one last piece of the puzzle. How does a QR actually write these points down? Well, each point is, at the end of the day, just a number. And every number, deep down, is nothing but a row of on and off switches. That is binary. So here is the final trick. Make every on a black square and every off a white square. And that, honestly, is all those little squares really are. Your numbers turned into a curve, sampled over and over, and written out in black and white. Which finally explains the magic. When you tear the code, all you're really doing is rubbing out some of those sample points. But you remember the trick now? The curve only needs a handful of its points to be redrawn, and the ones that survive the tear are still more than enough to pin it down. So you redraw the curve, solve straight back for every missing point, turn the numbers back into letters, and your link is perfect again. That is why a torn code still scans. And how much damage can it take? You actually get to choose when you make the code. There are 4 levels, trading space for toughness from about 7% of backup all the way up to 30. And once you understand this, you start spotting it everywhere. Those QR codes with a company logo sitting right in the middle, that logo is destroying a whole chunk of the code, completely on purpose. The error correction simply treats the logo as damage and rebuilds everything underneath it. And it scans every single time. This whole idea has a name. Reed-Solomon error correction, after Irving Reed and Gustav Solomon, who published it in 1960. It is the reason a badly scratched CD still plays straight through the scratch, without a skip. And it is how the Voyager probes sent crisp photographs home from billions of miles away. Out there, you cannot ask for a resend, so you bake all the backup in before you ever launch. And that is the deep idea worth taking away. Add enough spare points to anything, and no single piece of it is essential anymore. Damage just becomes noise that the maths quietly erases.